class. I think my internet is bad today, so we might have some issues, but um, hopefully not. So I was just in Spanish class, and we were practicing adjectives and like family members. Um, and so I said, we were practicing abuelo, and which means grandpa, and viejo, which means old. So I was like, I said, los abuelos son viejos, a no ser que hay teen mom, which means grandparents are old unless you have a teen mom. And it's so funny because it's all freshmen, so they don't know what I'm saying. I'm just like saying like random, like mildly inappropriate stuff, and I don't even think they look up what I say. So I just say weird stuff in that class. It's pretty fun. Okay, so I'm going to make a couple announcements. First announcement is your final is available. So you can take it now. I gave you 2 attempts. So between now and Friday at 11:59 p.m., you can take it twice. I will take the higher of the 2 attempts, and that will be your final grade. The final is 18 questions. I would say about half of it is on third triad stuff, and the other half is on, so it's like maybe a quarter triad 1, a quarter triad 2, and half triad 3. You can use notes, but I expect you to work alone. Let's see. I gave you 222 minutes to complete it. I don't think it's going to take that long at all, but I don't know. I gave you 2 attempts, so I gave you 222 minutes. I didn't want to move my finger off of the 2 key on the keyboard. Okay. And let's see. My hope was that this week, those of you who have missing assignments are getting caught up. If you have missing assignments that you want me to grade, you need to tell me via a Canvas message which assignments by Wednesday. Okay? Late assignments take me much more time to grade because it's grading, normally I'm grading in bulk, so that's very efficient. But when I'm grading individual students' assignments that are all over the place, I have to click between pages, and it takes me a long time. So I need extra time to do that. So you need to get me that information by Wednesday if you want it on your grade. And if you have a D or an F, I will allow you to redo old quizzes until your grade is a C. Okay, because I do not want anyone to. I think everyone at least should get a C in the class or have the chance to get a C no matter what. So, yeah. So I will repeat those announcements in the Zoom room after my review. So let's go ahead and get started. Hang on a second. So I'm going to continue my review. Hopefully you saw my review on Tuesday. And so I'm going to start off with reviewing momentum. So momentum is denoted by P, and it's equal to mass times velocity. Okay, it's a vector, meaning that it has a direction, so you can have a positive momentum or a negative momentum. The total momentum of a system is going to be P1 plus P2 plus ... however many masses there are. And so the reason that we study momentum is because it's really useful in collisions. So anytime there's a collision, you want to think about momentum first, conservation of momentum. So in collisions, the total initial momentum before the collision is equal to the total final momentum after the collision. Okay? So, you know, a lot of times we would have two objects hitting each other. Okay? And so the conservation of momentum equation for that would be m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Okay, so this is a conservation of momentum equation for a two-body collision. But and so you could solve for whatever you need to solve for. But we learned about something called a completely inelastic collision. And so for a completely inelastic collision, the objects collide and they stick together. Okay, so that means that v final 1, the first object's final velocity is going to be equal to the second object's final velocity. Okay, so excuse me. All right. So in that case, our conservation of momentum equation would be m1 v1 plus m2 v2 equals, now because they have the same final velocity, you're going to have m1 plus m2, because they're acting like a single object, v final. Okay, and so you could solve for v final or whatever you need to solve for. In a completely inelastic collision, kinetic energy is converted into heat. Okay? So that's why you could never use energy heat is a really difficult form of energy to quantify. Okay, you have to have a really well-designed experiment to figure out how much heat is being exchanged. Okay, so you can never, even though energy as a whole is conserved, you don't really that heat variable is an unknown. So you have to use conservation of momentum in a collision. If you wanted to know how much heat was dissipated, then what you could do is you could look at your initial kinetic energy, which would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. That would be your initial kinetic energy. And then you look at your final kinetic energy, which is going to be 1/2 m1 plus m2 v final squared. And then you would subtract those two because they're not going to be the same number. And that would be the amount of heat dissipated. Okay. So another area that was related to momentum was called impulse. Okay, and so impulse is denoted by J. And there were two ways to calculate impulse. One way is is just force times time elapsed. And the other way is if you have a force versus time graph, then the impulse is the area under the curve. Okay. So yeah. Now, why is impulse studied in connection with momentum? Well, it's because if you talked about the impulse due to the net force, the impulse due to the net force is, so that would be net force times time elapsed. That is going to be equal to the change in momentum of the object. So impulse and change in momentum are connected to each other. Okay? And in particular, we talked about the sneaky form of Newton's second law, which was that the change in momentum divided by the change in time is equal to the net force. So we use this equation to calculate the force of impact. If you see something hit something else and bounce off of it, you know the change in momentum because you know the initial velocity and you know the final velocity. And if you had a high-speed camera, you could figure out how much time that collision lasted for. And then you could use this equation to get the net force. Okay? So that is momentum. And so the next thing we talked about was circular motion. So if an object is moving in a circle, so here's the circle. That circle has a certain radius r, and here's the object, and capital T is called the period. And that is the time it takes to go around the circle once. So if you are moving in a circle, the velocity, or your speed, the velocity is going to point tangent to the circle. So wherever you are in the circle, the velocity is going to be tangent to that point. And then the acceleration is going to point towards the center of the circle. Okay? And so for that reason, it is called the centripetal acceleration. So when you are moving in a circle, you have what's called a centripetal acceleration. Centripetal means center seeking. So then we learned some equations. In particular, we learned how to calculate the speed if you're moving in a circle. So that was 2 pi r divided by the period. So circumference of the circle divided by time it took to go around. So distance over time. The centripetal acceleration we can't derive this equation. If you take my class next year, I'll show you why this equation is true, but it's equal to speed squared divided by the radius of the circle. So the faster you go around the circle, the more acceleration you have. We could combine, we could plug in for speed right here into that equation and get a second expression for centripetal acceleration. It's perfectly equivalent. And that is 4 pi squared r divided by the period squared. Okay, so you can use either one of these depending on the situation. Newton's second law is completely valid if you have an object that is moving in a circle. Okay, so if you have an object moving in a circle, you have net force equals ma, and for the acceleration, you would use the centripetal acceleration, so v squared over r, or you could equally well, you could use 4 pi squared r over period squared. Okay, and then this force is the force that makes you move in a circle, and so that is the called the centripetal force. So whatever force is making you go around in a circle, it could be any of the forces we learned about. It could be gravity, could be normal force, could be friction force, it could be elastic force, could be the electrical force. We'll learn about the electrical force later on. So it could be any of those forces making you move in a circle, and so whatever that force is, we would call that the centripetal force, and that's what we would plug into the left-hand side of Newton's second law. We learned about, horizontal circles. Okay, so a horizontal circle means that it's moving in a horizontal plane. Okay, my piece of paper is flat, so it's moving like that. Or we could talk, so for a horizontal circle, those are really easy. You basically just use this equation. All right, it's really simple. But if you have a vertical circle, so a vertical circle is like this, or from this perspective, it's, moving out towards the camera, then that is a little bit trickier. So I wanted to talk about vertical circles a bit. So for a vertical circle, so sort of like a Ferris wheel, the thing we have to be careful about is if you are at the top of the vertical circle, things are different from if you're at the bottom of the vertical circle. So in a horizontal circle, every point in the circle is basically the same. Okay, there's no difference between the two. But if we think about a vertical circle, gravity points down, which is towards the center of the circle if you're at the top. But if you're at the bottom of the vertical circle, gravity still points down, which is away from the center of the circle. So that makes it a lot more complicated. Not a lot, but just more complicated. Ivan, knock it off! Ivan! Give me 1 second. Ivan, don't do that. I have to put Ivan's food bowl on a table, or else Hazel here will eat the food. So it's up on a table so only Ivan can get to it, and he likes to bury his food, so he's like scratching the table to bury his food. It's annoying. Okay, so for a vertical circle, so now usually with a vertical circle you have a second force, so there are actually two centripetal forces. So you have, I don't know, maybe some force, I'll call it F right here. Okay, now if you're at the top of the circle, your centripetal acceleration is going to point downward towards the center. And if you're at the bottom of the circle, your centripetal acceleration is going to point up towards the center. Okay? So what would your Newton's second law be if you were at the top of the vertical circle? Well, your net force is going to be up force minus down force. So that's going to be F minus mg equals ma. So ma is going to be mv squared over r. But it's downward, so it's going to be minus mv squared over r. Okay? So that minus sign is really important there. If you're at the bottom of the circle, your net force is up force minus down force, so it's F minus mg. But now your acceleration is upwards, so this is going to be equal to plus mv squared over r. All right? So vertical circles are a little bit trickier for that reason, because gravity is switching things up on you. All right, so then we talked about gravitational fields. So a gravitational field is denoted by g, little g, and it's basically it's the acceleration due to gravity. It's the acceleration due to gravity. Okay, so gravitational field is another word for acceleration due to gravity. And the formula for the gravitational field is big G times big M divided by r squared. So what are these things? R squared is, well, okay, let's start with big M. Big M is the mass of the thing creating the gravitational field. The mass of the thing creating the gravitational field. So that depends on your perspective, okay? If we were talking about you and we wanted to know, you know, you're in the gravitational field of the Earth, then we would use the mass of the Earth. If you're floating in outer space under the gravitational influence of the sun, then this mass would be the mass of the sun. If you were floating above the moon, this would be the mass of the moon. So whatever is creating the gravitational field that you're experiencing, that is big M. R is your distance from the center. Of the thing. Now we have to be a little bit careful here because sometimes we talk about altitude, okay? And so altitude is not the same thing as distance from the center, right? So if we wanted to calculate R, let's say your altitude is A, that's your distance above the surface. So you also have to add, so you know, if this is the planet, and the radius of the planet is little r, and you're up here at an altitude a, then that total amount of distance is big R. The distance from the center is big R. Okay, so big R is your altitude plus the additional distance to the center, which is the radius of the planet, or whatever, what have you. Okay. Big G is a constant of nature. It's called the universal gravitation constant, and it is equal to 6.7 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, so once you've calculated the gravitational field, you can figure out what the gravitational force is. So the gravitational force is simply going to be the object's mass times the gravitational field. So this m is different from that m. Okay, this m is different from that m because this is the mass of the thing experiencing the gravitational field. So, for example, this is the mass of the satellite. This is the mass of the thing creating the gravitational field. This is the mass of the satellite. And this is the gravitational field the satellite experiences. Okay? Which depends on how far away from the center it is, right? Because as you get further away from the center, the gravitational field gets weaker. Okay? So then what we did is we started to talk about orbits, and in particular we talked about circular orbits. Non-circular orbits are beyond the scope of this class, so don't worry about it. Forget about it. Circular orbits, we have it's basically like a horizontal circle problem. We have net force equals ma. The net force is the gravitational force, because gravity is acting as the centripetal force. And then mass and our acceleration, we use the centripetal acceleration, 4 pi squared r over period squared. Okay? And so when we do this and we simplify the resulting equation, we get Keplers Law. Actually, that's Kepler's second law. There's 3 Kepler laws. But it is G m t squared equals 4 pi squared r cubed. Okay, so this is the period of the orbit, this is the radius of the orbit, so distance from the center, and this is the mass of the central body. That's important that you know this is the mass of the central body. So this is not the mass of the satellite. This is the mass of the central body. Now, so Kepler's law has 3 variables. It's got mass, it's got period, it's got radius of the orbit. And so if you know 2 of the variables, you can solve for the third. So for example, let's say you knew the mass of the Earth and you knew the radius of a satellite's orbit. You could calculate the period. So how often is that satellite going to come around, so you can look at it with a telescope or something like that. If you knew the mass and the period, you could calculate the radius. So this would be used in the orbital calculation of a satellite. Let's say you want a satellite to go up into space and have a certain orbital period. Like maybe you want the orbital period to be 24 hours, which would be called a geosynchronous orbit. So you would plug in period equals 24 hours, you know the mass of the Earth, and then you can figure out how far up do you need to put the satellite. I think the coolest way of using this equation is if you know the period, because you can figure out the period of a satellite just by looking at it through a telescope and seeing, it went around once, okay? If you know the period, and you can use a telescope to figure out the size of the orbit because you're just looking, and is it going like this around in a circle, or is it going like this around in a circle? So you can figure out the radius, and you can use that to get the mass of the central body. So this is how you would do things like determine the mass of Jupiter, a planet. Because you can't take Jupiter and put it on a scale. Too tough. All right, so that's my review for today. On Tuesday, I will review rotational stuff. So that was the last topic, is rotational dynamics. And then you guys will be set. Remember, you can take the final twice. So if you feel confident about the rotational stuff, then I would just take the final once over the weekend or something, and figure out what questions you have, and then you can study that, or you can ask me about the topics. Okay.